A very good afternoon. I'm really glad, and it's my pleasure again that in a quick succession, physics department is organizing very effective and what should I say, very relevant webinars. So if I'm not wrong, perhaps in a very quick succession, Department of Physics of Scottish Church College, they have organized quite a number of webinars and talks, which are I believe, which are so effective for students and also the faculty. Today, the department is organizing a webinar on multiscale modeling of complex systems. Our esteemed speaker is Professor Prabal Maiti, Center for Condensed Matter Theory, Department of Physics, Indian Institute of Science, Bengaluru. So, Professor Maiti, I welcome you, most cordially welcome you on behalf of the college. As the principal is now engaged in a meeting, so I am giving this very short welcome address. One thing must be noted once again, that really I am happy that the Department of Physics is continuously busy with such activities, and after a long interval we have opened our colleges and universities, but still we cannot accommodate all the students in the on-campus classes, in-person classes. So we have to depend so much on the virtual mode, and thanks to the virtual mode, of course not thanks to Corona, COVID-19, but of course thanks to the virtual mode, that we can invite and we can organize so many such webinars and other talks on virtual mode. Let it be very clear that my knowledge about this is just one, that this relates to solid mechanics, and if I'm not wrong, this is perhaps this particular topic, complex systems and multiscale modeling, this has also an angle of international relations, because in the 1980s, if I am not wrong, United States, they took up a new policy, and since then, this as a discipline and interdisciplinary activity became rather popular in the academic parlance since the 1980s. So that way, being a social scientist, I am rather interested about that particular aspect, that it is interdisciplinary and it is also related to international, to one particular aspect of international relations. Otherwise, this multiscale modeling of complex systems, this is too complex for me. I am from social science, so if I try to say more, then that will be betraying my monumental ignorance about this. So I welcome you, Professor Maiti. I congratulate all my colleagues, head of the department, Professor Dr. Joita Choudhury, and all my other faculty members. And I encourage my students from the physics department to participate more and more in such webinars. And I hope this is going to be one more success for the department. Thank you.
Thank you so much, sir. Now I request Dr. Rupendranath Nandi to conduct the technical session.
Okay. Respected Principal Ma'am, Dr. Madhumanjari Mondol, respected Vice Principal Sir, Dr. Supratim Das, and my dear brother IQAC Coordinator, Dr. Samrat Bhattacharya, HOD, Dr. Joita Choudhury, other colleagues, my dear students. Today, we are lucky enough to have Professor Prabal Maiti from IISc Bengaluru to give a lecture to our student, to the department, to other colleagues. Okay. I feel myself very privileged to introduce the speaker today. Professor Prabal Maiti is currently the chair in the Department of Physics, Indian Institute of Science, Bangalore. Professor Maiti received his MSc and PhD degrees in physics from IIT Kanpur, India, followed by postdoctoral stage at MP, IP, Mange, the University of Colorado at Boulder, and Caltech, USA. In between, Professor Maiti did his post-MSc at Saha Institute of Nuclear Physics. He is my classmate. I feel proud of him. He is a fellow of Indian Academy of Science and recipient of Alexander von Humboldt Fellowship and Fulbright Fellowship. He is also an associate editor of journal PCCP, Royal Society of Chemistry. It is a matter of pride that his H index is 44. And I was talking at the beginning that his citation is nearly 7,000. It's really a great matter for Professor Maiti. And currently he is having 171 publications. He collaborates with Professor A.K. Sood, the great experimentalist, Professor Chandan Das Gupta, and Professor William A. Goddard from Caltech, Department of Material Science. He works in the area of multiscale modeling of soft and biomaterials. Areas of current research interest include structure and dynamics of hyperbranched and conjugated polymers, charge transport in molecular systems, DNA-based nanotechnology, and confined fluid. Today, Professor Maiti will be speaking on multiscale modeling of complex systems. Professor Maiti, please. Hello.
ওদের একটু টাইম ল্যাগ আছে
মনে হচ্ছে প্রবাল শুনতে পাচ্ছিস?
Now I can hear you. In between I lost you. I don't know if it is at my end or your end.
Oh,
I lost in between for a minute or two. For a minute probably I cannot hear you.
no problem. You start, my friend. Okay.
Oh, okay. Okay, yeah. So good afternoon, everybody, and I really feel privileged to be part of this afternoon colloquium at Scottish Church College, and I'd like to express my sincere thanks to Dr. Supratim Das, Vice Principal, for the welcome, and Dr. Joyita Chattopadhyay, ISOT Physics, and of course to my dear friend Upen for making this possible. It's really nice to connect and see each other after a long time. So with that, do I have the permission to share? Let's see.
Yes.
How do I share screen? Yeah, I got it. Just give me a moment. Share screen. And then this one. Share. And I make it full screen.
Yes, we can see it.
Open. Is it visible, everything?
Yes, everything okay.
Yes, it is visible.
Okay, thanks. So yeah, so I won't be able to see during talk if anybody raising hands or, but Upen or Jaita, please help me. I can stop anytime because the interaction is most important, and if anybody has any question, I'll be happy to take during the talk itself so that we get clarified. Okay, so feel free to interrupt me for asking any questions and clarification. So what I'm going to talk about today, a very interdisciplinary topic, as Dr. Supratim Das rightly pointed out. It's really interdisciplinary. The complex system. I'll be defining a complex system, and in fact, climate science, social science, they are also part of this complex system. But in my talk, I won't be talking about those, but I will talk about some other systems. So before I start, I just want to acknowledge several students who have worked on a variety of problems, which I'll be talking over the years. Biswarup Mukherjee, then Hemant Kumar, who is with Biswarup now in Sheffield. Hemant is in IIT Bhubaneswar. Maid, currently at ISC. And then I'll be talking about some work from Jeet. Jeet finished his BSc in Scottish Church in 2017. And right now he's pursuing his PhD in my group. And Subodh, let me take a pointer. Just okay, yeah, and Subodh, so and then Abhishek, Sayantan, Himangshu, who is Sayantan is now in KIT Germany. Himangshu now in IIT Hyderabad. Santosh in IIT Jodhpur. Supriya, he's about to finish. And then as Upen pointed out, I collaborate extensively with the various colleagues of mine and ISC or outside ISC, Ajay, Chandan, Manish, Bill Goddard at Caltech, Nate Seaman. Unfortunately, he passed away just last week. Yamuna Krishnan, earlier she used to be at NCBS, now she's in the University of Chicago, and Samtai Lin at Taiwan University. So here is a brief outline of the talk. I'll be talking about giving some history and introduction to multiscale simulation, what exactly they mean. And then I'll talk about, pick up 3 different complex systems, and one is confined fluid. So I'll define what is that fluid and how do you confine it. And then I'll be talking about charge transport. Actually, this should have been coming. Charge transport in a molecular system. So I'll be talking about electron and hole transport in a molecule, and particularly in a molecule like DNA, RNA, and so a very fascinating behavior. And then if I have time, I'll be talking about creating nanostructures whose building block or basic elements are DNA. So if you look at Wikipedia, so Wikipedia actually will define a complex system in the following way. So complex systems are simply concerned with the behaviors and properties of a system. And a system can, and that system exhibit properties that produce behaviors which are distinct from the properties and behaviors of parts. So it's like a collective behaviors which the individual constitution may not show. These system-wide or global properties, we have characteristics of how the system interacts. So there will be interaction between these individual components with or appear to its environment or of how it's behaved and etc. So this is what a Wikipedia definition of a complex system, which can include the confined fluid, charge transport in a molecular system, social network, and climate science. All these are part of this complex system. In fact, this year Nobel Prize was given. I'll come back to that. And then all these complex system study will be doing in a multi-scale. I will do study in a computer simulation, and there I will define what exactly is a multi-scale simulation. So the tools will be classical molecular dynamics and Monte Carlo simulation, and in some cases it's a quantum version of this. So here I was telling that the Nobel Prize in 2021, which was announced last month. So Paris is a physicist, and these 2 other gentlemen, Klaus Hasselmann and Manabe, they are the climate scientists. So their citation read for groundbreaking contribution to our understanding of complex systems. In fact, these 2 gentlemen, Klaus Hasselmann and Manabe, they are pioneer in modeling the climate. And Parisi did modeling of several other complex systems, including liquid, glass, spin glass. Okay, so those are example of complex systems. So the field of this multiscaling is a truly interdisciplinary, and this one is exemplified this Nobel Prize in 2013. These three gentlemen got Nobel Prize, and the citation read for the development of multiscale models for complex chemical systems. So you can see the citation 8 years later for our understanding of complex systems. And in this case, it's again a complex but chemical system, and that's what I'll be talking about today. And again, a multiscale model. So these are the two keywords, multiscale model and chemical systems. And here you can see the nature of interdisciplinary. This gentleman is in Harvard Chemistry Department. Levitt is a computer scientist, works in Stanford Computer Science and also structural biology. And Warcel, he is a chemist in the University of Southern California. Prior to this, so what I'm trying to highlight that this is a truly interdisciplinary and very mature field. A lot of work and innovation has gone into this field. And so the prior to that was another very, very fascinating development, and which again got a Nobel Prize in chemistry in 1998. So Walter Kohn, who expired some years back, he was at University of California, Santa Barbara, and John Popol, he was in Northwestern, and their citation read for Walter Kohn for his development of the density functional theory, and this one is actually very, very valuable for the multiscale modeling development. And then another major milestone became a commonsman tool. Commonsman in the Common Technical Man School is the development of computational method in quantum chemistry. So all of you know who are doing quantum mechanics that we can solve analytically a model Hamiltonian, a model potential, simple harmonic oscillator, step potential or delta potential. But for a truly many-body interacting system, we can write down the Hamiltonian, but we cannot solve it even now. And so then this gentleman, John Popol, actually he put together a framework, and this framework is in a code called Gaussian, which allow you to do actually quantum calculation for many-body interacting system. And so now the field, as I said, that the field of molecular dynamics has a rich history, and there is a great Indian connection. And I would like to highlight that Anishur Rahman, who used to call himself a Hyderabadi. So he was from Hyderabad, and he passed away in 1997. And he actually did a pioneering work, and that is supposed to believe to the birth of modern day molecular dynamics simulation, for which these other three gentlemen got Nobel Prize in 2013. So this is the two seminal paper Anishur Rahman wrote while he was in Argonne National Lab. One is this first modern atomic molecular dynamics simulation. This is the first modern atomic MD simulation on liquid argon, and showed variety of liquid structure properties, which actually is verified experimentally. And then finally, some years later, almost 7 or 8 years later, in 1971, the first molecular dynamics simulation of liquid water was done and shown very interesting properties. Okay. So what is molecular simulation? And because I'll be talking about a multi-scaling complex system, so I need a model of system. So we actually in computer, giving any phenomena or any chemical system, we can build models. And models can be your chemical structures. If you have here I'm showing a liquid crystal molecule which has liquid phase, liquid crystal phase, and crystal phase. So this is a liquid crystal molecule which can be modeled either at these chemical details, or you can model it as a simple, like physicist simple model in two interpenetrating cylinder, or what is called a spherocylinder. Okay, so this is what is a model. Okay, and on these model we can do computation. So again, to emphasize that if you want to do a computer simulation like a theory calculation, you need a model, and on that model you can solve that model either through an analytical or a computation. So here is another model of what is called a lipid or surfactant, and it's a chemical model. But you can do a physicist model, make of this head and hydrocarbon chain connect with spring. So this is what is called a bead spring model. So these are the how you exactly the model various chemical system at different level. Either where you look at all the chemical details of all elements, or you get rid of those details and make a more coarse grain. So the coarse graining here is what is called a coarse graining, and say higher level model. And here I am showing like molecular model of proteins, DNA. So these are molecular models for some biomolecules, okay, which can be used to do your calculations. So what are the, so that is the model. So how do you solve this model? Once you have these models, then you have two different kind of simulation And that's where the concept of multi-scaling comes on. One model is what is called a semi-empirical, gives us the phenomena and invent model, what I was telling, that if I want to look at the water properties, then I'll build a model of water and then study their dynamics and structures using some model, that model. And on the other hand, there is this method what most of you are learning in your BSc or later MSc you'll do, that ab initio method. So Maxwell has given us a set of equations to describe a variety of fields. Boltzmann has given equations to describe transport or other entropy concept or many other. Schrodinger equation you can write down and then solve. So these are what I call the ab initio. You can have the equations, you solve it, and sometimes they work for a system, sometimes they don't work, and many a time you cannot solve that, unfortunately, for a complex systems. So what this multi-scaling, what I'm going to talk today is that can we bridge this, because this is coming from the phenomenology, the microscopic you can write down, and this is what is a phenomenological, giving a problem, you try to hook up or invent a model. And I would like to bridge these two. And how do you bridge that? So here is what is a bridging, and this is what is called a multi-scaling strategy. So what you do, that you solve a quantum mechanical problem, okay? And at that level, you talk about electrons, nuclei motion. So all of you know, or many of you know, that we talk about, say, Born-Oppenheimer. So nuclei is moving in a sea of electronic degrees of freedom in the nuclear electronic potential. And so this calculation, as I'm telling, that in quantum mechanics, you cannot solve it because it gives rise to equation too complicated. You can solve it only on a single electron level. Okay, many electron, you cannot solve it. You have Hartree-Fock, beyond Hartree-Fock, and then this density functional description comes into picture. So since we cannot solve this problem at a very, very higher many electron systems, so what we do with the question we ask, can we actually integrate out all the electrons? So the nuclei will move in the effective field of electrons. Okay, and that's what you know is a Born-Oppenheimer, because nuclei is heavy, slow, electron are fast. So you integrated out electron and nuclei is moving in the field of electron. And that's what is give rise to a molecular dynamics. Okay, so in a molecular dynamics, we throw out electronic degrees of freedom. We talk about only nuclei degree motion in the effective potential of electron. And that's where we come here. So here, no electrons are involved. We talk about atoms, which are nothing but the nuclei. And that effective interaction from those electrons are calculated from the quantum mechanics. And many a times, even at that level, and here you see, I'm showing you the level of calculation and the time and the size you can access. So here, we cannot do more than a few angstrom, which is longer molecule. Here, few nanometer, and with the time scale, the time evolution, we cannot access more than, say, nanosecond or beyond. Sometimes with a larger computer, we can access microsecond, but not beyond. So in many cases, what you do, you course gain further. Okay, so you say that we no longer talk about individual nuclear, individual atoms. We say it's a group of atoms is a pseudo atom. So this is what is called a mesoscale. Okay, so here you can see that I am now grouping up a group of atoms and making it a pseudo atom. And then we'll be talking about the interaction between these two and then look at their property. And at this length scale, we can go about millimeter, talk about a big grains, we can talk about second time scale. Okay, and even at this length scale, we are limited. And then we go to a continuum model. Okay, so many of you might have heard the Landau, Ginzburg, Hamiltonian. So there we talk about the order parameter or a density field, etc. So here, that's why you solve a continuum model, and there you can go to millimeter beyond length and time scale of minutes. So you see that. So the underlying, so the interaction or how you get the density field or order parameter field is actually all the way coming from the underlying quantum mechanics. So that's the basic, and then from here you go all the way here, treating this at different level. And this is what is called a multi-scale modeling. Okay, and that's what we do in our lab to solve various problems, various complex systems. Okay, so the different technology or different kind of methods at each of these level are highlighted or listed here. So here you solve a quantum mechanical problem. Okay, you solve many-body Schrodinger equation here in computer because you cannot solve it in analytically. And then what you do that when you are no longer can do that even in computer, then you do MD, and then the interaction involving these various nuclei, what is called a force field. So different forces acting on between two nuclei in a molecular system. So you calculate from here, and then you do a molecular dynamic simulation. Okay, and then in the mesoscale simulation, there are what is called a coarse-grained molecular dynamics, dissipative particle dynamics, Brownian dynamic simulation. So these are the technical terms for different simulation methodology which are working here. And then finally, in the continuum model, you do a macroscopic modeling. So many of you might have done finite element or finite difference method, continuum simulation, or using what is a modern day simulation called lattice Boltzmann. So these are different simulation techniques bridging this length scale and time scale all the way from angstrom scale quantum mechanics, electronic degrees of freedom to the continuum mechanics. Okay, so this is truly what is called a multiscaling. So then I'll be talking about a molecular dynamics, which is right after quantum mechanics, the next methodology or techniques. So there, you know, all of you know, high school, that this is the equation I'll be solving. So the difficulty in this equation, the force is mass multiplied by acceleration. So the difficulty is actually in this force. So what are these forces? Okay, so as mentioned that these forces has to be computed from quantum mechanics. Okay, so once you have done that, then what you can do, let me see if I can, oh, this movie you are supposed to play. So you can see this is a protein motion I am showing you. So here I am solving the coordinates and velocities for each of these atoms as a function of time, which is evolved through these dynamics, this simple equation, but the forces are calculated from this underlying quantum mechanics. Okay, so then if it is a molecular system, apart from, so what are the different forces? So you know the different degrees of freedom. So you have this bond stretching, and you have this angle bending, then you have a polyatomic system, then you have this dihedral motions, and then you can have this inversion symmetry in a molecule, like in ammonia, you have this inversion symmetry. So these are the different bonding or interactions termed in your system, which you need to actually take care of the forces and the energy associated with this while solving this equation of motion here. Okay, this equation of motion. Here I have just written down various terms, or how do you actually model these potentials. So bond stretching, we can use a harmonic bond. Okay, and then angle bending, you can do again harmonic angle. Here I am writing a different form. Then torsion is a dihedral here, and then inversion is here. And these terms, the force constant for the bond, and then the equilibrium bond length for all the elements in a periodic table, okay, they are computed using quantum mechanics. Similarly, the equilibrium bond angle for different angle in a involving 3 atoms, and then involving this force constant for that, again, this k theta and theta 0, these are actually obtained from quantum mechanics. So similarly, for the dihedral is represented as a Fourier series. You need a 4-body term to maintain, say, certain symmetry in the molecule, or the planarity, for example, benzene ring, etc. So then these are what is called a force field, and these are derived from quantum mechanics. Similarly, you have other non-bond interaction where you have a Coulomb. If you have a charged particle, for example, water, H2O, 2 hydrogen, 1 oxygen, they have all charged species. So then there will be Coulomb interaction. And so you need to know what are the charges on these hydrogen and oxygens. So again, you know, charge is a quantum mechanical concept. So you have to actually derive the charges in the molecules from quantum mechanics. So from there, and that's actually a hard problem, and still evolving methodology development, how to get the charges in each of these atomic species in a molecule quantum mechanically very accurately. Okay, and then there are other interactions, the dispersion interaction, which we either van der Waals or Lennard-Jones potential. So these are the different potential, and then if you know the potential, you can take the gradient, you can calculate the forces and solve the Newtonian dynamics and get the position and momenta, and then you invoke statistical mechanics and then calculate all thermodynamic properties. So that's what is the simulation methodology. Now I am going to use this to tell you a couple of very interesting problems. Any question, comments? Okay. Feel free to interrupt me and ask questions, okay, if something you want to get clarification. So having said that, I'll first let me tell you very fascinating world of this confined water or confined fluid. So many of you know that the water in a bulk phase, if you take a bulk ice, is a hexagonal symmetry. So the bulk ice is a hexagonal ice structures. But then this paper some years back in Nature, what they showed that the water inside carbon nanotube, and you can see they have, these are all ice structures, and they have different symmetry than the hexagonal ice. Okay, and so what I mean that when you make ice confined into narrow space, 1D confined or narrow carbon nanotube, okay, which are diameter of say 1 nanometer or 1.4 nanometer or larger, say 2 nanometer. The confined ice has a different symmetry than the bulk hexagonal ice. Okay, and and then another very interesting experiment was done through neutron scattering again. So here the neutron scattering experiment was done on a 1010 nanotube. So here is around 1.4 angstrom nanotube, and then there you can see that this ice structure on the surface of the nanotube, and there is a central chain, and they get this structure by solving the different intensity pattern that which matches the structures, and this is the proposed structure that in neutron scattering experiment. So two things, that the ice structure is different, and second thing is that water enters nanotube. Okay, so then I will tell you some interesting features of this confined water which may not be available or which is not seen in bulk water. Okay, so here for example I am showing you our simulation. So here I am showing you this one. Yeah, so here is a long nanotube, very narrow nanotube. Okay, so this is a 6.6 nanotube, around 8 angstrom is the diameter of the tube, and in that diameter only the water can enter single file. You see that water is forming a single chain, and because of the confinement, water cannot cross each other. Okay, so they are in a single line. This is what is called a single file motion. Okay, and here I am showing the same in a bundle form. So the nanotube is in a triangular lattice, and so I am showing you just on the side. So here you can see that water is forming is SFD, single file chain, and this chain, these are I am showing at room temperature. Okay, so they are supposed to be liquid, but if you calculate, so here I am showing you the filling fraction. So oops, this was a movie supposed to play, didn't play. So here I am showing, for example, how many water is entering through the nanotube. So you see this nanotube is around 20 angstrom, 2 nanometer long. So on an average, there are 5 to 6 water molecule all the time. So as soon as you put this nanotube in the bath of water, water spontaneously enter, and we'll talk about why it enters, because there is a thermodynamic penalty in spite of that it is entering. So we'll come back to that. But here you can see on an average 5 to 6 water always inside this nanotube, and they form this nice the single file chain. And here, if you are making different diameter, as I was showing in the previous ice structure, so you can make 5, 5, 6, 6, 7, 7, 8, 8. These are chirality of the tube, and chirality of the tube making different diameter of the tube. And so these are the different water structures you will get inside this nanotube, and they have very interesting properties. Okay, so one interesting property. So here I am calculating the axially projected the pair correlation. Like if you all of you have seen solids. So if you solids atoms are in a specific lattice point, so there will be sharp, well-defined peak. Okay, at each of the lines. So there you can see, and this is what you see similar well-defined peak at different locations on the axis of the tube. So this is like a solid. So we are talking about a solid-like ordering of water inside nanotube at room temperature, and this is happening because of the strong confinement. In liquid, in a bulk box of water or a bucket of water, you won't see this. There will be liquid only first peak and then no ordering. But in confinement, you see this very, very well defined. So this is one of the surprise because of the confinement. And another surprise is that they all move collectively. So if one is going on the left, everybody follows. Okay, so here I'm showing you the trajectory. Everybody in the movie might have noticed that they follow each other. Okay, so this is a collective motion. So in the strong confinement, making the movement collective. Okay, so the individual diffusion you cannot talk about. You have to talk about diffusion in a collective sense, that all of them going either left or right. Okay, it's a collective motion, and that has very, very strong implication in their dynamics. I'll skip this. These are, I mean, more. If someone wants to understand more, I can talk about. Then quickly, I'll talk about what Jit recently did. Jit is from your college. So here, so in 2015, there was this very interesting science paper from Andre Gaev group from Manchester, who got Nobel Prize for graphene. How many of you might know? So what they showed a very, very fascinating thing. I was telling so far, no, that bulk ice is hexagonal ice. Okay. Now what they did, they see the ice structure between two graphene sheets. So they have two graphene, and in between the two graphene layer, you have water, and at some high pressure. And what they showed here, I'm showing their experimental image, and what they showed that inside this capillary, water from square size. So the symmetry is square symmetry here, not the hexagonal symmetry. And this was a surprise. And the question is why it is happening. Can you understand this? So Jeet actually went ahead and did this work, and we published it early this year. And so here is Jeet simulation that you have two graphene sheets and is bath in a water bath, and then you see the confinement is such that only one layer of water is inside the graphene capillary. Okay. So question is that what is the structure? What is the ice structure inside? How do we characterize it? So what Jeet did? So what we did, we looked at different. So I was telling, no, you have to have models. So for water, we have many models. So we looked at all possible model existing in literature, if not all, many. So we looked at 6 different models. It looked at 6, and for variety of models. So these are the name of the model. So you don't have to remember that. But what you message is that water is a 3 water. I mean, this is 1 oxygen, 2 hydrogen. So 3-point water model. But it turns out that if you want to produce water properties, all water properties, which has many anomalies, then sometimes you have to invoke a 4-point is a model, what is called a T4P. So apart from that, in all, so what is the message it got, that all the 3-point water, they form this nice water structure, and he characterized it. And so that a way to characterize would be what is called a quadric order parameter defined here. So this is a 1 water and then this neighbor. So you can define such a order parameter. And once you have this quadric order parameter, if it is high, that means it has a square symmetry. And that's what Jeet calculated. So this is what is showing the quadric order parameter, very high order parameter. And here it's showing the distribution of this angle here, and all showing the appearance of a square ice structures. So indeed we see that when you confine a layer of water or ice inside 2 graphene sheets, tightly confine it at certain distance, then they form a ice structure which is different than hexagonal ice, and that's what we also see in our simulation. Then Jeet went ahead and did many other things along with another students, Subhadeep. So they calculated the dielectric constant. So all of you know that the water is a polar liquid and it has a large dielectric constant. In fact, many of its interesting behavior is coming because of this large dielectric constant, which is around 78 to 80. But here you see is a very interesting behavior once you have this confined it in this, and then it's an order structure. So dipole fluctuation are suppressed. And because of that, you have an anomalously low dielectric constant. So you see bulk would have been at 80, and here you see a dielectric constant 2 to 3. So this is really remarkable that you can actually get such a low dielectric constant water or ice phase when you confine it and make an order structure, and the dielectric constants appear to be such a low. And this is what you also they see in experiment, and this is what they get in the theory or simulation. Then I come back to very fascinating questions that why waters. I showed you that as soon as you put the water in nanotube bath, nanotube in water bath, water spontaneously enters. So many of you might have heard that the nanotube is a hydrophobic channel. Okay, so hydrophobic meaning that there is a loss of, there's energy penalty gain to enter a polar molecule inside a confined. But still they enter. Okay, so what we showed that this is because of, this movie should have played. For some reason this is not playing. Yeah. So then we showed actually that that this is a rotational entropy gain which is allowing the water to enter. Now all of you or many of you have done in statistical mechanics BSc, you solve say the classical ideal gas, write down the partition function, calculate thermodynamic quantities. Or many of you might have done also harmonic oscillator, calculate the partition function and write down the other thermodynamic quantities. But apart from these two, no matter what level of advanced statement you do, you'll see that you cannot solve anybody interacting Hamiltonian to write down the partition function. Either you have to do some approximation. Apart from that, you cannot do. So here is a complex system, anybody interacting, how do you calculate entropy? Okay. So for that, you need to calculate the different normal modes. So here are the different normal modes of water. I'm showing you here. So these are the normal modes, and these are Raman active. If you do a Raman experiment, you will see the associated intensities peak. And these Raman modes, what is called a density of, you can calculate the density of states associated Raman mode, and each of these density of states will contribute to the entropy of the system, and then we can calculate that entropy and show that is a rotational motion which is contributing to this entry of this water inside this nanotube. Okay, so these are more technical, so I'll not go into the details, but I can discuss in private. Okay, yeah, this is related to how you do this partition function for such a interaction system and how you calculate entropy. So these are some details. Okay, I just kept it in case someone asks. So I'll skip this. So then this is what we did. So what you see that in experiment, so using these we can, so experimentally entropy is here. Okay, so 60 or 70, okay, is the entropy, joule per mole per Kelvin. Okay, that's the units. And then using our theory, we are getting more or less the same entropy. And using this technique, we actually calculated the whole entropy from vapor to liquid coexistence. So here the lines are experiment. Okay, so entropy, and this is the different points. So this is the triple point, this is the critical point. And then you can see that all our calculation using different model, they more or less agrees. Okay, so we have a very, very robust way to calculate water entropy. Okay, and comparing well with the experiment. So then with that, this is what I was telling that, so in this nanotube, this is the bulk. Okay, so here, so bulk water, when it is there, so the enthalpy of the water molecule is these units are written here, and this is the translational entropy, this is the rotational entropy, and the Helmholtz free energy is this. Now, as soon as you are entering into this confined 6,6 nanotube, which is 8 angstrom diameter, the enthalpy loss, correct? This is a hydrophobic channel, it's losing the neighbors, it's one single file, it does not have the other two neighbors. And then this is the translational entropy, which is very similar, but then you see the rotational entropy gain, which is compared to this. So if you add this, your Helmholtz free energy is very similar to the bulk, and that's why it does not feel any penalty, water is entering. So this is what is came out from our calculation, that is the entropy which is driving this entry into the nanotube. Okay. So I'll this then another interesting problem we are recently we're doing, Subhadeep also involved, that if you have a flow in, so what was the problem? So some years back, Professor Ajay Sudhina lab in our department, they did this experiment that if you put a nanotube under tap and keep on increasing the tap water flow, and then you have electrodes between the two ends of the nanotube, then you can create voltage. So here I'm showing you the voltage as a function of velocity, flow velocity, and you can see they can generate voltage. Okay, so question is that what is causing this? So we wanted to understand this, and so we are mimicking same simulations. So here you see this is the nanotube under, so the flow is tap water is flowing now through the nanotube. This is the flow happening, and we calculate the voltage. Okay, so in our language, voltage is nothing but we look at the dipole alignment. So how, and that the giant dipole we can create a field. Okay, so this is what, and this is what many of you might have the say for example spin in a magnetic field, and you calculate say Langevin function, the magnetic field. So similar proposed Langevin function we do, and we can see what is the average dipole moment as a function of flow velocity, and then that actually will be responsible for this flow induced voltage. Okay, so this is another interesting. So what came out from our calculation, that flow acts as an effective field to align water molecule inside CNT, which can in turn, okay, generate this voltage, etc. Having said that, I'll now switch gear and come to another very interesting topic, again multiscale. So this is what is first transport in a molecular. So all of you know the electronics, the semiconductor industry. Okay, so these are silicon based. So now last several years there's a big push to actually replace silicon with different other molecules. Okay, so one organic molecules. So here are the different elements. It can be any other organic molecule. So here the idea is that between electrodes you will have this molecule, and the question is that what is the transport or electronic or hole transport through such molecular junction? That's the field of whole molecular electronics. And the experiment, what the different techniques are the STM break junction. So you bring a STM tip and tip on this molecule and look at the signature and calculate the IV characteristics. Okay, so that's the way you characterize this. Okay, and these are also here, or sometimes you can bring a AFM cantilever and do the same thing and calculate the conductance. Okay, So we wanted to understand that how such single molecule can conduct electricity or conduct currents, or can it be used for other thermopower device or variety of other applications. So this is what here, for example, I'm showing you a graphene junction, okay, 2 graphene electrodes and single molecule, and then they can also act as a single molecule junction. Here they can act as a molecular diodes. In fact, I'll show you that how DNA can act as a molecular diode. So between 2 electrodes, you have a DNA molecule, and they can actually act as a diode. Here, molecular thermoelectron device, as I already mentioned, variety, and then it can actually switch. Okay, that can act as a molecular switch. So I want to see that how this previous the multiscale simulation technique I was describing can be used to actually study some of these interesting systems. Okay. So yeah, so for our purpose, our molecule will be DNA. So then here I'm showing a diode made of DNA, and they have variety of interesting applications. For example, using these, you can detect the mutation in a DNA. Okay, so detection and then through electrical signature. And then the ultimate goal is to have functional DNA chips. Okay, so that's why we would like to understand the electronic properties or conduction properties of a nucleic acid, namely DNA, RNA, and other nucleic acids. What are the mechanism of transport? Okay, so again, I'll skip this. So this was again a Nobel Prize winning work from Rudy Marcus many years back. So he actually solved this problem that how an electron can actually, the conduction can happen in such a system. So this is like a diffusive, so you have these different sites, okay, hopping sites, and electron can hop from one side to here. So different hopping sites, electron can hop, and then you have a conduction. And the idea is that how to calculate such conductions and characterize the IV characteristics. Okay. So here is what is I'm showing you. So in this schematic, you can see that electron can hop from one side. If it's a DNA, you can see DNA is a helical structure. So this electron or hole can go from this to here, here to here, here to here. So these are the different hopping sites, and you have to calculate the hopping matrix. Okay, and that's what is a truly quantum mechanical calculation, and it's a very, very expensive calculation. And this is what I was I wanted to show you this here. So this is what Marcus solves as hopping, how to calculate this hopping matrix. And so we calculate using this multiscale modeling that hopping. And once you have that, then you can actually calculate conductance in a molecule. Okay, so and then other way would be what is called a coherence transport. That was a diffusive transport. One can actually have a coherent transport, and for the coherent transport, you need to do a full quantum mechanics calculation. The molecule is between these 2 electrodes, and you have to calculate the Fermi function because of the attachment, and then you can calculate Green's function. So these are technical details, but I'm just telling you what are the elements there. And once you have done that, you can calculate again conductance. Okay. So with that, here is our system. So here are the 2 electrodes. These are normally gold electrodes, and then a DNA is attached to such gold electrode. Question is that how is the conductance of this DNA varying as a function of the length of this DNA? If you have a mismatch or some mutation in the DNA, or you have something interconnected between DNA, which is a variety of situations. So that's what we can actually talk about. Okay, so here is again multiscaling. So what you do, you have a DNA in water, DNA they remain in aqueous environment. We do a electronic structure calculation using quantum mechanics to get that the overlapping, that the hopping rate, etc. Okay, and then we do a kinetic Monte Carlo to calculate this IV characters or the current through this molecule. So here, so before I do that, then there was some experiment where people. So here is the experimental results that people calculate the resistance of the DNA. So you can see these are. So again, there are no clarity whether DNA is a semiconductor or metal, or sometimes there are reports that it can be superconducting also. So here, more or less, you can see that the resistance of DNA, it's in a mega ohm range. It's actually increasing with the length of the DNA. So base pair is define the length. So it's more or less a length of the DNA. Okay. So question is that can we actually reproduce a behavior and then predict various other interesting behavior? So this is what we did recently. So here is our calculated using this multiscaling. So here we are calculating the current versus voltage for DNA and RNA. This is a short DNA. This 4 base pair will be around 1.5 nanometer long. This 12 base pair around 4 nanometer long. So what you see, so this is what is the current for a DNA, through a DNA between 2 gold electrode. And see, DNA is always better conducting than RNA, okay? Whether in a short DNA or larger DNA. Another interesting features you can see the bias voltage. So for a short DNA, you need a really small bias to get the current. Here you can, on the other hand, you see that for a longer DNA, you need a really large bias to start current. So this is like acting like a diode. You can see that. So the DNA length dependence. Okay, so you can have length dependent bias, and they can act as a diode. So there's a truly electronic component in your circuit. So that's what, and one can see that the amount of current or the magnitude of current, they actually matches with the experimental results. Okay, let's see some chat. Someone is asking. Okay, so I'll come back. Someone has asked something. I'll come back quickly on this. Let me. Okay. So yeah. So what our result shows that DNA has a higher conductance than the RNA, and that's what is coming back from our calculation. Okay. So again, we you can explain this why it is happening. So I'll not go through those details because those will be boring. So I just want to leave a message that this is what can happen. And then I'll take quickly another 2 minutes to actually give another fascinating piece of results what are interesting many of you. So DNA actually is a polar molecule. If you are aware that DNA 2 ends are different. Okay, so in a terminology, it's called 5' 3' end because it's terminated with different chemical units. And then DNA can be actually elongated by pulling. Okay, so these are fascinating experiments you can do either using an optical tweezer or AFM experiment. Okay, so these are called single molecule experiment. And here I am pulling DNA or RNA into different ways because it's a polar molecule, you can pull different ways. So I'm showing you different ways. And then as you are pulling, you can calculate this current. So here I'm showing you the current as a function of stretching length. How you are. So here again, I see that this is what is again the different way I'm pulling the DNA. And as I am pulling, I'm calculating the current as a function of this pulling length. And here I am showing you this. So here you see the current as then there is a sudden drop. So as a function of the stretching length, current suddenly goes from a large value goes to 0. So depending on how you pull, you see that here is a stretching length is only around 1.6 nanometer. But here you see where the current goes to 0, it's almost double than that. So depending, so one can, and this kind of pulling actually you can detect, or this kind of structural transformation. So here you see the DNA structural transformation. So this structural transformation you can actually get through this electrical measurement. So if you have a shorter pulling length where the current is dropping to 0, that means you have this kind of pulling. On the other hand, if you have a larger pulling length before the current goes to vanishes, then you have this type of pulling. And these actually you can see from this type of calculation. Yeah, so this is what. Then quickly I'll tell you a fascinating. So far I talked about only carbon nanotube, but you can create nanotube using DNA, and this is what is fascinating. So here you can create nanotube, DNA nanotube. So this is a hexagonal packing. So you can have 6 double helix forming a hexagonal bundle. So this is a hexagon nanotube from using DNA. You can have 8 double helix forming this octagonal DNA, and they have different properties. So you can have different diameter of nanotube depending on the different amount of the different numbers of the elements in the cross section. Okay, so this require a lot of software design. So I'll skip that. So how you make that? So this is what the way we do. So here, so this movie will explain. So we need to create first to stitch 2 DNA. Okay, so how do you do that? So this is the first DNA, and then you have to stitch another DNA. This is the second DNA. We create that, and then we do a Monte Carlo. We bring these 2 DNA together and enumerate all possible energetic configuration along this where we can connect. Okay, so because you have to connect the 2 backbone to connect them. Okay, so here we have identified the low energy configuration, and what we cut and nick. Okay, Ni can connect. So Ni meaning connect the phosphate and connect to the other. Okay, so this is what is happening in a Monte Carlo way. You can see this. Yeah, so you can see that for these two, what that is, the two DNA has been stitched together. Okay, and you can see, I'll explain quickly. So here, so this so this is the way you can do a DNA tiling. Okay, like a graphene lattice, you can have a DNA lattice. So this is like the two unit DNA lattice. So you can see that this blue DNA, which was supposed to go like this strand, it has make a crossover here. Similarly, this red, which was supposed to go like this, to make a crossover here. So in the process, you have 1, 2, 3, 4, 5, 6 crossover. And now you can bring a third DNA, but then and want to make a lattice, and then they can fold to create a nanotube. Similarly, the graphene lattice, and they fold and they make a nanotube. The same philosophy here. Okay, so using these, you can actually, so this is what is now a lattice of 6 such DNA, and then they can actually fold and give rise to the nanotube. You can see this. Okay, so this is what we have now, a DNA nanotube, and you can see, and you can calculate the transport or variety of things what we did for carbon nanotube, and also you can look at the various other interesting mechanics. So here is a DNA nanotube, 6 helix bundle, and it's these are the ion environment, and simulated in water, and we calculate their stretch modulus, Young modulus, and see how stiffer are these. Okay. Yeah, so here, and then to make it little more stiffer, we make a pillar. So we saw that here, for example, you see that the ends are kind of fraying, not able to maintain their tubular structure well. So the idea is that can you make a stiffer, then you make beams. Okay, so these red DNA are the beams flanking these, and there are 3 beams here, there are 2 beams, and these beams are made of DNA, and we can show that they make it stiffer. So for example, the stretch modulus, okay, which is nothing but if you multiply this by the area, you will get the Young modulus. So here around 6,000 piconewton, but if you put pillars, they become 10,000 piconewton. So make them rigid. Okay. So with that, so so we did many other things, but then I'll just tell you one more interesting last one, that with this DNA fascinating world, you can create variety of other nanostructure. So with this DNA, you can create what is the most symmetric structure, which many of you might know, that's icosahedral symmetry. So here is the icosahedra, and so these are all vertices and all are made of DNA. Okay, so this has 20 faces, 12 vertices, 30 edges. So this is the characteristics of icosahedra, and we want to build such icosahedra use a high symmetric object using DNA, and that has many purpose for drug delivery, for cancer treatment, and this is what we did. So this is a DNA icosahedra we experimentally done in Jamuna Krishnan lab experimental design. So here is our icosahedra made of DNA, and we can actually calculate. So this is their image of a icosahedra, and they give you the diagonal length, and we make the model, we calculate the diagonal length, and they matches with this experiment. So this is a computationally built DNA icosahedra. This is the experimental TM image, and they matches, and then we do various calculation on this DNA for many other applications. Okay, with that, I will end my talk and take questions. Okay.
Thank you, sir. Dr. Shubha Shamanto. Shubha, please conduct the question answer session.
Yeah. Okay. So it's the time for question answer session, and sir, you can see the chat box.
Yes,
several questions.
Yeah,
several questions are there.
Yeah.
First, I want to ask a question.
Yeah.
You have shown some plots showing the order parameter. So how to calculate the order parameters, or actually what is the order parameter?
Yeah, so this is one I was talking. So if you have various order parameter you can calculate, but in this case, because we have it's a 2D order parameter, because in a 2D confined system, I'm talking. So this is the probably we're talking about, correct?
Yeah.
This is what is called a quadric order parameter. So here, so the question is that how. So if you pick up any water and then ask the question, how is the neighboring water? Are there any specific arrangement of that? Okay. So that questions can be answered by calculating this, what is called a quadric order parameter. So if K, this one is 6, then it's a hexatic order parameter. If it is 4, it's a quadric order parameter. So if this is the value of the order parameter, and if it is a square order parameter. So then this one will show a large value. Okay, the k is equal to 4, and that's what is the order parameter. So here is this is the way it's defined here. So you calculate this angle, and then you calculate this quantity and average over all the water in your system, and then you have this number here.
Okay.
Does that answer your question?
Yeah, sure.
Okay.
Sure.
So this is a order parameter which will say that if it is a square order structure, for example, here. So if you can see pictorially that this is square ordering, so this value will be very large. On the other hand, here you see that there is no such order. For this, the psi4 value will be very low. As you can see here, that here, for example, psi4 is close to 1, but here, for example, it's close to 0 or very low. So that's what is the order parameter. Okay. So you need the order parameter which is close to 1 in a phase and close to 0 in another phase when the disorder phase. That's what it means, order parameter.
Okay.
Yeah.
Okay, let's move on. Oritrojit has asked a question.
Where do I
You can
see?
see.
Chat. Let's see. Yeah, chat. Yeah. So let me go back to this. Yeah. Can you please elaborate a bit more on the 4-point structure water and also on the thermodynamic penalty in the water? Yeah. So Ritrajit, the 4-point water you see. So the water. Oh, with this chat I cannot. So it turns out that if I just take 3-point, like in a chemical species like 2 hydrogen, 1 oxygen, that water model cannot reproduce, for example, many times the correct, say, density anomaly. You know, the water density has an anomaly at 4 degrees, correct? And so that, or the associated with the density anomaly, the diffusion, viscosity, all of this is anomaly at that particular temperature, correct? And so that many of those properties cannot reproduce by this. If I just take 2 hydrogens and 1 oxygen, so many times to reproduce the correct diffusion, correct the density anomaly, etc. Sometimes one put an off-center point, which I was showing here in this. Here. So this is just a model and which reproduce. So here. So this is the original 3-point water, the 2 hydrogen, 1 oxygen. But here I put a off-center kind of interaction site. This is another interaction sites basically, which helps us to reproduce many of the anomalous properties of water. Okay, that's what is the 4-point water. Does that answer your questions? They can unmute and talk or not?
Sir, can you elaborate a bit after that off center, because my internet connection got lost.
I see. No, so what I'm telling that this is just a, so there are actually 5-point water also. So these models, so you see, I was telling that's the philosophy, that you have a phenomena. You have, for example, the density anomaly of water, correct? Or the diffusion anomaly or the viscosity. So, and you want to explain that behavior. So if you just have the 3-point water model, like 2 hydrogen, 1 oxygen, that cannot explain that. So question is that, can I actually modify my model? So the way to people figure out that if you have the off center, you saw that here, this site, I cannot go, here. So here, for example, this is actually another interaction sites here, which actually helps improve the density anomaly compared to this. That's what I'm telling.
Oh, okay, sir. So, but what, like, you are saying that that is the interaction point, but like, what do you mean by that? Like, you have, and my question actually came from, I saw that M, like in between 2 hydrogen atom. So that is where my question, what is that M? Like, what do you signify with that M there?
That's not, this is another sites where I have interaction which can have a charge here, okay? And that's what is denoted by the M site.
Oh, okay, okay.
Yes,
sir.
yes. Does that answer?
Yes, sir. Yes, sir. And
sir, what was the other question you were asking? Go ahead and ask.
Yes, sir. The other point was that thermodynamic penalty you were talking about in nanocapillaries, and along with that, does that manifest itself in any way to the water rise we see in capillary tubes that we have studied in high school? And
very interesting question. In fact, this one asked when I gave a talk in PRL Ahmedabad also. Many plant scientists were asking. In plant also, you know, plant has this capillary.
Yes,
the
sir.
water rising.
That during that transpiration, there is
Correct,
a pull.
correct. So I don't know actually, Ritraji, if we have some connection, but definitely. So how exactly water level in the capillary rising? There must be this entropic and enthalpic, what I call competition, but I cannot comment on that unless we do this. So here, what I was showing or trying to tell you that this nanotube is a hydrophobic channel, correct? And because the water does not like to enter into the hydrophobic cavity. That's the general notion, correct? But here you saw that as soon as you put a nanotube in a bath of water, water spontaneously enters. Okay.
Yes,
so then,
sir.
if there is we know that because of the hydrophobicity of the channel, there is energy penalty. Correct. It loses energy. But then, why is it that the water enters? So then we saw that then something must. So it's the ultimately the free energy has to be minimum. Correct. In thermodynamics, you talk about free energy. So enthalpy is one of the components. So we showed that because although it's losing this energy, but it gains because of this faster rotation, because of the losing of the hydrogen bond from the other two neighbors. So then this rotational entropy gain, and then it makes the total Helmholtz free energy same as in bulk. So for it, the free energy is not a penalty. That's what we showed here. But how exactly it relates to that capillary, we really don't know, but it's an interesting question. We should certainly look at it, yes.
And sir, last one, something that came to my mind right now, that is, even if it's not connected, like let's say it is not connected somehow, and it can, like we describe it with Newtonian mechanics as we do using surface tension and adhesion cohesion. So like what is the limit? Like what is the limit where that we can observe that what you are saying, that with the thermodynamic penalty, this is more observable, and the ordinary ones where we study the water rising capillaries. So where is the limit? That is it a like smooth translation?
It's another very, so this one relates to my other part of the talk where I'm talking about a flow through nanotube. You must have seen. So how I am generating the flow? You saw that I create a pressure gradient.
Yes, sir.
Correct. So I have a high pressure and low pressure. Okay. And then you saw that the water flows. Okay. And in that, so there's a competition. The flow is acting like another aligning field, correct? So that pressure difference. And then there are this temperature fluctuation due to the temperature, correct? So as you are there aligning, they're losing entropy, correct?
Yes, sir.
And then the temperature will like to make it disorder. So there is this competition, okay? So so how exactly they will manifest between these two? This is an interesting question. So I don't know actually the correct answer to this. What will be the limit? But there will be this competition.
Okay, sir. Okay.
Yes.
Thank you, sir.
What was the other? Let's see the chat box. This one, Ritajit. Then someone asked, Pritam, you can ask.
Pritam, are you there? Ritam, unmute yourself and ask.
Yes, ma'am. Yes, ma'am. Actually, there was an internet issue.
Pritam, please go ahead.
Sir, like I want to ask a question that only organic compounds can be used in molecular electronics, or other type of compounds which are non-polar or inorganic, they can also be used or not?
Yes, they can be.
Okay,
in fact, there is a worldwide effort to actually generate correct molecules which are more thermally stable. What you are asking, actually stability is one of the issue which should not be degraded so easily in a large wide range of temperature or other environment. So there are worldwide effort to generate or to synthesize more thermostable molecules. I cannot hear you. It's a lot of noise. Hitam?
Yes, sir. It's not from my side.
Okay.
Thank you, sir.
So it is. I mean, so there are many other. I am picking up a specific DNA because DNA, so one of the main bottleneck in this whole synthesis is the polydispersity. Okay, so we are talking about a single molecule, correct? So you need to have a great control over the synthesis of that molecule, correct? So that you exactly so when you want to generate a certain length, Yeah, so in polymer, for example, if you want to synthesize a polymer of certain monomer length, if you are aware what is a monomer, the atomic weight, molecular weight, etc. So you end up actually synthesizing a distribution of molecular weight. Okay, not exactly the one you want, but a distribution. So the control over that synthesis rather is very difficult in many cases. But DNA molecule, the synthesis is a very well controlled. Okay, so you actually can have a very monodisperse, meaning if I want a 14 base pair or a 15 base pair of length, say 4 nanometer or 5 nanometer DNA, one can actually get enough only that, not any distribution of length. So that's why DNA has this very fascination for variety of application, and that's why we are trying to use that. But there is no limit that does not preclude other inorganic organic molecule for this purpose.
Okay, sir. Thank you, sir.
Yeah. Any other questions? Let's see.
The next question from Obishang Pal.
Visham, go ahead.
So my question is that you talked about the usage of DNA in electronics. So
yes,
I want to know that, means from junior classes when I was in school, it was said that the DNA molecules can be subjected to, means they can easily break if they are exposed to radiation for a long time. And we are using them in electronics. So definitely some electromagnetic radiations are bound to be present in the circuit.
No,
so
very interesting question. In fact,
how long do we expect it to remain stable there? Or how much feasible is it?
No, that's a very interesting. DNA melting temperature is around 70 degrees centigrade. In a normal condition, DNA melts around 70 to 80 degrees centigrade. Okay, normal B-DNA. And when I say normal B-DNA, let me show you this DNA. It's an interesting question, some applications. So I'll just see if I give you this DNA. Can you see this?
Yes, sir.
So if I just, this is what is called a B-DNA. Okay, it's a right-handed helix. Okay, DNA can have a left-handed helix also, but here I am using a right-hand. So this DNA, the melting temperature is anywhere between 70 degree to 80 degrees Celsius. Okay, and what you are telling, if there is a radiation, then the damage can happen. That this, in fact, we are also studying that the damage, radiation damage. So the base pair can mutate actually. When I say damage, either oxoguanine damage can happen, or this base pair actually between it, some other mispairing can happen. So those are possibilities. But then what one can do, one can actually design other component. That's what in fact is my here. So one can design this kind of DNA which are much more, so whose melting temperature is much higher. So these are more thermostable, mechanically more stable. In fact, this is what. So for example, I'm showing you a DNA which is generated from 2 double helix, and this has a much higher stability both in terms of thermostability and also mechanical stability. So there are these ongoing process that you can use actually other higher stable DNA. And then I show you can even stabilize better by generating bigger complex structure like this. Okay, this has even higher melting and higher mechanical properties. So you can actually generate more complex object with the same DNA as a building block, which has more thermal stability, more mechanical stability. All those can be taken care of. But your point is valid that those can be an issue. Correct.
And
but
sir, is it economically feasible?
What yes. I mean, people are, I mean, these, you mean economically feasible means the synthesis?
Means sir, the general usage, because scientifically many things are very promising, but at the end everything comes down to the economics.
very interesting point, but I'm forgetting your name. Tell me.
Abhisham.
Abhisham, so it's a very valid point. So economy of course, is a big player and big decision maker. But the many discovery happens that way. I mean, initially the economics may not be obviously visible, but then at the end, I mean, if that was the case, then the development of MRI or AFM, this will not happen. MRI, for example, has revolutionized the whole medical. So the initial research, although they are like what you are suspecting or is not clear, correct? So that will come at a later stage when it go to at a technological stage. So the technology, this has not yet gone to the development of a technology. So only at that stage one can talk about economics. At this stage is very difficult.
And sir, can you please once again explain that how the two DNA strands when placed laterally they were joined together?
So here, so this is a in experiment. So let me show you in experiment what they do. So here, so I'll play this again. So in experiment, what they do, so it's a very controlled way. So they bring this 2 DNA, okay, and then what they do, they detect actually through an enzyme that these are the sites. Let me get a pointer here. So then they detect that this is a cross. So these are called crossover site, okay. So these are, for example, the 6 crossover site, okay. Then what they do, once they detected, then what they do, this is what they done. They actually cut it. So they cut these sites, the phosphate linkage. So when I say cut, the nick. So in the terminology of the technical, it's called the nick. So you, like a scissor, you cut those phosphate. So these links are cut, okay. Then what they do, oops. So the cutting has already happened here, and then you nick and then you connect. So this is where you connect. So then the strand which was red, which was going like this, now they do this, okay. So a crossover. This was which was supposed to go like this, they make a crossover, okay. So this is the way you have 6 different crossover. So this is experimentally they do it, okay. And this is the same thing we replicate in our model building in computer. This is what I was showing you. So that in computer, we have to do so what we do, we detect those sites, crossover sites, by enumerating the energy. So because it has to be a minimum energy configuration, ideally it's a free energy, but here we talk about energy only to build the initial configuration. So we see that what is taking one helix here, we rotate the other helix, okay, and try to see what are the minimum energy configuration at this junction, and then that's what once detected, we do the same thing, we nick and connect. And that's what you can see. We are nicking it and then connecting it. Does that answer your question?
Yes, sir. And so one more thing, means there it is written px65 molecules. What does this px65 mean?
Yeah, so you have all interesting questions. So px stands for here. I'll explain here. So here you can see one. So count the number of base pairs. Okay, 1, 2. So here count here. Okay. So here it's a 5 and then 6. 1, 2, 3, 4, 5, 6. So in between 2 crossover, you have 6. So here you have 6 bases. So 5, 6, 5, 6. That's the way. Do you see it?
Yes, sir.
So you can actually, so that way you can now change the crossover location. And experimentalists are seeing that is it the every 6 crossover, is it the stable, or every 7 crossover, or every 8 crossover? So because you are asking, how stable are these for our electronics application? So you can actually generate. So people do 5-5, px7-5, px8-5, px9-5. So this is the terminology, and we have modeled it, people have synthesized, and we show that the 6-5 is the most stable one. I did not go through all of this. So this is the terminology. So we calculate the free energy as a function of this, how many bases are in between 2 crossover. Okay.
Thank you, sir.
Any other questions, comments?
Excuse me, sir.
Yeah.
I have a question, that is, you have shown a plot for water that is plotted along the axis of entropy versus temperature. Can you please explain what does that plot represents?
So it's where, let me just try to get at where is that entropy. No, not this one. Where is it? Where is it? Entropy. Here, this one, correct? So what is the questions?
Sir, what does this represent actually?
No, so this is what is a experimental. So this line is from the, the NIST database, National Institute of Standard, okay, at USA, who maintains all the experiment, even the standard time, etc. They have this database, what is called a steam table, okay. So if you go to NIST database steam table, they have this table for the experimental determinants of entropy of water in liquid phase, in vapor phase, okay.
Yes, sir.
So that's the entropy. I'm plotting it here, that in the vapor phase you have this entropy, in the liquid phase you have this entropy, okay. And this is the critical point here, and this is the triple point. The water phase diagram has both triple point and critical point, correct? In the phase diagram, if you do OT phase diagram, you have the water, there are phase transition, and that's why in that phase diagram you will have a triple point and critical point, correct?
Yes, sir.
So this plot, what it is showing, that if you have take this water and have vapor phase and liquid phase, and the question is that the experimentally they determine the entropy of these different phases as a function of temperature. This is what is experimentally available. So now when you develop a theory, so your theory should be able to reproduce that experimental results, correct?
Yes, sir.
So that's what the so other theory earlier was not able to reproduce. So these points are our theory. These red points and these other points, you see, these are our theoretical calculation using this method, which I did not explain because of the technical. So here, so what I was telling, that water has, normal modes, correct?
Yes, sir.
Normal. So here I am showing the normal modes of, like you might have done in solid state, 1 chain atom basis, 2 chain atom basis, correct? So there you calculate the normal mode of that system, correct?
Yes, sir.
And so here I am showing, if you take a water molecule, what are the different normal modes of the system? And these are the different normal modes. These are the different normal modes. Okay. And these are, you can calculate, or you can get, you can experiment and detect this using IR or Raman actually. Okay. So if you do a Raman, you will see these peaks here. So you will see a peaks at 400 centimeter, 4000 centimeter inverse, which is related to this normal mode. If you, and the peak around 2000 centimeter inverse, this relates to this angle bending, and so on and so forth. So now all these, so these are normal modes. So they will contribute to the total entropy of the system, correct? All the modes, all the motion in your, all the internal degrees of freedom, they will contribute to the entropy of the system, correct?
Yes, sir.
So then, so question is that how do you take care of these modes, okay, into calculation of the entropy? So that's the question we ask, and we have developed a theory which I didn't, it's a technical, so I didn't go through that. So if you put together everything, then you will get these. This is the entropy table, and here number wise I'm showing you here that in at 300 Kelvin the steam table, so the experimental entropy is 70 joule per mole per Kelvin, correct? That's the correct unit of the entropy.
Yes, sir.
And then, and this is what is our calculation depending on this different water model. So this with 3-point water actually is agreeing quite well with this experimental number. And so, and then for other temperature, this is what this is telling, that not only at 300 degree you agree, for other temperature also you get a close agreement. That means that we can use this theory to talk about entropy in various other environment. That's the point I'm trying to make. Does that answer your question, or maybe I'm not getting what exactly bothering you?
No, sir, it's okay. I understand.
Okay, okay. In
Okay,
fact,
so
the,
no, I think there are no other questions. So I request Joitadi to end the session.
So I answer, let's see.
Okay. Rita is here.
Yes. So I request Dr. Upendranath Nandi for formal vote of thanks. Sir, please.
Okay. So let me thank the speaker for his beautiful presentations on the multiscale of a complex system, multiscale length scale of complex systems. We thank the principal ma'am, vice principal sir, IQAC coordinator, our colleagues, and my dear students. I thank the other organizer for their support for this webinar. And we have seen the Professor Maiti has presented a beautiful things on the new systems. Particularly, we are fascinated to have the collaboration within the department, both theoretical and experimental side. I feel very interesting in the sense that Professor Maiti has tried to simulate the experimental results done by, obtained from the experiment by Professor A.K. Sood. Okay, particularly the confinement of water within the carbon nanotubes and the reduction, strong reduction of dielectric constant from 80 to almost 3, I think, almost 3. It's a beautiful result, beautiful result. Also, the electronics at the molecular level, at the DNA level. Okay, that is a very, very fascinating result. And we are thankful also to our student Jit Mojumdar for contributing at least a small part to the work done by Professor Maiti in his group. Okay, so let me thank again Professor Maiti for his beautiful presentation, and to all the participants for their patience and hearing. Thank you all.
Thank you, Upen, and thanks everybody for your time and listening. I'll be so drop me an email if you have any further question, comments, or any other help, whatever. Okay, I'll be happy to interact.
Okay. So students, it is my maybe request. Okay, so try to collect the email ID of Professor Maiti from our head of the department, Dr. Joyita Chaudhary. Then if you have any questions, he's my close friend. He will not mind at all. If you have any questions, email him, you will get the answer. You will get the answer. Okay?
Yeah, you can come to our website and get my email ID or Google it. So it should be available. Yeah.
I'm giving the email ID in the chat section. Okay.
Okay, fine.
Yes,
Yeah, that's Gmail.
you
and
can
also,
note.
yeah.
So we are ending the session.
Okay.
Yeah.
Thank
Okay,
you, sir.
thanks everybody.
Thank you so much.
Thank you. Okay. Okay. Thank you.
Okay, bye.
Bye. Bye. Bye, Prabal. Bye.
Bye. Bye.